As we've seen, operators are pretty important, so let's take a look at how they play into pretty important in quantum mechanics. So let's look at see how they get represented in this Bra and Ket vector notation of Dirac. Just to recall, remember operators. I'm going to represent here as M. As we'll see, they turn into matrices in the Dirac Bra-Ket notation, and so I'll use M here as sort of suggestive of that. But for right now, think of it as just a quantum mechanical operator, and essentially they are a transformation that maps a function, a state, quantum mechanical state, into a different state. And the way we'd write it in the Bra-Ket notation is pretty much like we'd written it before in terms of the wave function. It's just this operator operating on this Ket vector to give us, in general, a different Ket vector, which I indicated with the prime here. For finite dimensional cases, and again, this might be a spin 1/2 system in which you just have spin up and spin down, so that's a quantum system that can be represented, and maybe a state in it is like this. Then one can transform in a linear fashion. Remember, all the operators in quantum mechanics need to be linear. The way one can represent that is with for this two-dimensional case is a 2x2 matrix, and so when I multiply this 2x2 matrix times this column vector, think of the Ket as a column vector, it gives me, in multiplying out the usual matrix multiplication, a different state vector that again is in Ket form, which is the column vector form. However, in all the previous work, if you remember, we didn't write these things out as operators. As we wrote them out as operators, but not as matrices. In fact, we had the operators were typically derivative type things or multiplication type things. For instance, the momentum operator was h bar over I times the partial with respect to x. That gives the momentum in the x direction. And at least in one dimension, the Hamiltonian operator was given this expression where V is some potential function. But we'll see how to generate matrices from these kinds of things a little later. But for right now, let's just look at properties of these quantum mechanical operators. And just to recall, some of these we've already seen. In general, quantum mechanical operators do not commute. They might, but in general they do not, so they're generally not commutative. And so A, B, at least there's no guarantee that that's going to be equal to BA if you change the order. However, they are associative. And so if I've got A times B times C operators, I can associate these two and multiply them out, operate with those, and then do a C, or I could do the B and C first. So the order in which you apply the operators in a product doesn't matter. And sort of related to that, I'll add a few other things that will be useful as we go through. If I have an operator to the nth power, this is sort of notational. That just means multiply the operator out n times, and one of these things is just, for instance, if n is 3, then I'd have A times A times A, or operate A, and A 3 times. And likewise, I could do any, where n and m are any integers. And obviously the product of these two, applying them using the associativity of it, is just this operator A done n plus n total times. You can use that to good advantage in getting really functions of operators. And the way functions of operators are defined is in terms of power series representation. So I know the representation of the function e to the x, so I can form the e to this operator A by doing a Taylor series expansion for e to the x, and then everywhere there's an x, just replacing it by A to get this expansion. Should go without saying, that lots of times we sandwich operators in between two states, quantum state functions. And pretty obviously, this operator just produces a psi prime, and any the this bracket for any two operators is in general a complex number. So this, in general, for a given matrix between state functions is a phi and psi between a bra and a ket. So you bracket it again, and what generally pops out is going to be a complex number. We only want to look at linear operators, and that's what ties us really into matrices. If you come back and you look at all of these properties, I could just as easily have been talking about matrices. In general, matrices don't commute. Matrix multiplication. Matrix, the order is important. But I can associate them. I can form powers of matrices. I can even form functions of square matrices. So all of these things, I could pretty much say the same thing for matrices. So we're led to getting this matrix idea of these operators in the Bra-Ket notation. Linear operators. We require linearity of all the operators in quantum mechanics, and that just means that if I add the two, if I had two quantum states, and then operate on both of those with a matrix, that I can operate on the matrix on the first one and add that to the matrix on the second. That should be an AM there. Should be an M there, so make sure to correct that. Or I could do it from the other direction as well. Here would be a general Ket vector, and you do that, and you get it from that direction. So either side works. And that's the first part of linearity. Second part is if I multiply a complex number times the state, then I can pull it through M because it's a linear operator. And likewise, if I multiply a complex number times phi, I can pull it out and just have the matrix operating from this direction and having the complex number, complex conjugate of the complex number that's in here. I remember we had expectation values of operators that figured pretty prominently. And in general, the expectation value is the bracket of the operator between the state and divided by the bracket of the state with itself. That's in the case if this is an unnormalized state function. A lot of times, though, we look at a normalized state function, and in the case of a normalized state function, if I have an unnormalized one, I can just divide. This is a number here. In fact, it's a real number. I can divide both of these by that real number and get a the square root of that real number, and get a normalized wave function. And in those cases, when I know that I've got a normalized wave function here, then the expectation value is, like we've been doing earlier, is just the bracket of that matrix operator bracketed between the Bra and Ket for that state. Actually, both of these are useful, and sometimes we'll do it in this form, and sometimes when we've normalized our states, then we'll use this form here.